mapping between IP4 and IP6. Obviously, in an ideal world, we'd like to see everything IP6 and all this IP4 to go away, but that's not going to happen for an awfully long time, if ever. So one of the things we have to do is do some mapping between them in some places. So I'm going to try and go through what the hell I'm talking about, why you'd want to do it, how I've done it, and some of the other ways of doing it. And the picture on the right is straight from our April Fool's joke. That's the connector cable for legacy equipment between IP6 and IP4. So, okay, I'm talking about a device that has IP packets on one side and IP6 packets on the other side. And one of the really obvious points that I spent ages trying to explain to one of my less technical friends was that an IP4 packet has IP4 source and destination, and an IP6 packet has IP6 source and destination. He seemed to think I could magically make a packet that had IP4 one end and IP6 the other, and obviously you can't do that. But a device that can do some mapping between the two, which sounds simple. Why on earth would you want to do this? Well, I got involved in this not because of trying to do IP6 only networks, but because we make kit and we've got boxes that will do general purpose mapping of IP addresses and ports. Very useful tools to have in any small network or even a large network where you can just handle something on one IP address and port and make it come out as another IP address and port. Very useful for moving things around or getting you out of sticky situations you weren't expecting. So that's a general feature of our older products. New products are all IP6 from the ground up, so I had to do some sort of mapping for that. So I had to map between IP6 and IP4. The other reason you might want to do it, and probably the more interesting bit in a way, is a side effect of this is you can make a general purpose mapping, something that will allow machines that only have IP6 addresses to access older IP4 machines that are still out there in the rest of the world. And there's quite a few techniques for this. Horrible acronyms, NAT-PT, NAPT-PT. I'll go through some of the techniques later, but a lot of them need some way to translate between IP6 and IP4 at a packet level. But before you can even start with that, you need some way to get a machine to think that some IP4 host can be accessed via an IP6 address in the first place. So you need to bugger about with the DNS. Basically, you have an IP6 only host with an IP6 DNS resolver, and it asks a resolver for the address of some host. So you might want to go to www.bbc.co.uk, which I don't think has an IP6 address. The resolver goes and gets the IP4 address from BBC's DNS servers. It then creates a fake IP6 record claiming that the BBC have actually got an IP6 address. And it returns that to you. Now, IP6 address space is nice and big, so it's quite easy to embed the original IP4 address in the end of the IP6 address you give it. So there's no sort of session tracking needed on the DNS to do that. And finally, obviously your laptop or browser will then connect to this made-up IP6 address, will get to your mapping device, and eventually be mapped to IP4. There is a downside. We're all trying to do DNSSEC and sign zones, and immediately we've got a box that's messing about with your DNS. It's doing a deliberate man-in-the-middle attack on your DNS by creating new IP6 records that didn't exist. It's not going to work with DNSSEC. So the only way to do it really is to have the resolver take out all the DNSSEC records and not have it. But this is something of a backward step, and I'm sure people who know more about DNSSEC can tell me more about this. But it's one of the slight snags with the whole idea. This is a diagram from the Trick or Treat Daemon. Yeah, that was a brilliant name. And it's an open source DNS ALG that does exactly this. It's slightly ironic that, apart from the fact they haven't used the IP6 documentation prefix for their diagram, they've actually got Google as the IP4 only host. And if, like us, you've got IP6 pairing with Google, they do have IP6, so it's a really bad example for it. But as you can see on the diagram, basically you have a machine talks to the Trick or Treat Daemon server, and it talks to the real DNS server, changes the answer, and your IP6 only host talks IP6 to a gateway, which converts it to IP4. Yeah, you get the idea. It's a bit messy. So having sorted out your DNS, you've now got an IP6 host trying to talk to an IP6 address that doesn't really exist because it wants to get to an IP4 endpoint. So the box gets IP6 packets one side, and all we've got to do is change the header from IP6 to IP4, haven't we? I've been told off for putting simples in a slide already. Far too many meerkats. Okay. One of the problems with this is, as I said before, the IP4 packet has its own source and destination IP4 address. So we need to think about how we pick the new IP4 source address. And I'll come on to that in a moment. We've also got to think about packet sizes. The IP6 header's bigger than the IP4 header. 40 bytes instead of 20. Causes a slight problem if your packet's already 1500 bytes long. It's going to get too big. The protocol layer, UDP and TCP, has checksums, and those checksums include the IP address. So they're going to be wrong. And of course, if you're changing source addresses, you're effectively doing network address translation. So you have to think of some way to track the replies correctly. So you're going to have to change some of the ports in the protocols. And of course, if you're doing any sort of NAT, it's got problems. As it says, NAT is evil, it's horrible, it causes havoc. But there's no other way to do it with this, really. So if we look at the headers themselves, it's not quite a one-to-one mapping. We're going to have to bugger about with the IP addresses anyway, as I've said. We can work out the new destination IP4 address because we shoved it in the IP6 that came from the DNS. There's type of service and DSCP byte in IP4. There's a traffic class byte in IP6, so we can kind of assume they're the same, although they're not necessarily exactly the same meaning. Time to live, well, we all know that looks like a hop count. It's not actually the same meaning, but it's good enough. IP4 has fragment offsets and IDs. You have IP4 fragments. IP6 has a complete extra header for fragments that again makes the packet even bigger. You can map those across mostly, but the IDs are a different size. 16 bits in IP4, it's 32 bits in IP6. In theory, there are IP4 options. Now, I'm glad to say that we really don't see IP4 options. I mean, I looked at some of the RFCs. It's possible to mark an IP4 packet as top secret, apparently. Thankfully, we don't see them very often, and so kind of ignore them and get away with it. Now, if you're making a firewall, one of the things you often do is drop any packets with options because they could be someone trying to exploit something. IP6 has got a flow label. I'm not 100% sure quite how anybody uses that yet, but it's not there in IP4, so you kind of have to ignore that as well. Even little things like the packet length is defined differently. In IP6, it's the length of what comes afterwards. In IP4, it's the length of the whole packet. So you have to adjust that as well. And then finally, the protocol ID in IP4, well, with IP6, it's a next header ID. So similar logic, but not quite the same. So you have to mess about quite a bit mapping between IP4 and IP6 just to get the headers right. Now, I mentioned source addresses. There's quite a few ways of looking at this. One thing you could do is a one-to-one mapping. You could decide that every active IP6 host that's using this gateway gets its own IP4 address, at least temporarily. That is one possible way to do it. And it would work with almost any protocol then. You wouldn't have to change the ports. It's not like NAPT, it's NAT. And it's going to cause you problems, though. You need far too many IP4 addresses to make sense. You might as well just give everyone IP4 addresses, except there aren't many left. So you can't really do that. So you're going to have to do some sort of NAT. Now, we could work with a pool of addresses, and that is one way to handle a large-scale network address translation. The problem, if you don't know, is that there are only so many ports in TCP and UDP, and you're having to use these to track the sessions when they come back. And if you want to handle more than 65,000 sessions, you run out of ports, so you have to start using lots of IP addresses, potentially. The other way of doing it is to go with a single IP4 address, but actually overload the ports. So instead of saying you're looking just at the port that's coming back, you're looking at both ends, the IP addresses at both ends, the ports at both ends. And that lets you use the same IP and port at the translation end for more than one session because it's going to a different place at the other end. Now, obviously, this doesn't work if you've got 65,000 separate sessions all trying to go to the same endpoint somewhere. Now, fortunately, places that are that popular, Google or whatever, have lots of endpoints and lots of IP addresses. So there's a good chance they're not actually all going after the same IP in the first place. It's one of the things we don't really know how well this idea of using a single IP is going to scale. But it has some interesting side effects, which I'll come on to in a moment. So what we've chosen to do is go for a single IP4 address. So anyone using our NAT gateway for this appears to be from the same IP address for everybody. Now, of course, as soon as we start doing this, we're going to have to change the ports inside the protocol header. So we've already moved beyond the IP header itself. We're now looking into the protocol, UDP or TCP, for example, and ICMP, so pings. And we have to change the ports in there. So protocol header. As soon as we change the IP address, we're already having to change the checksum because they include the IP address. Now we're changing the ports as well. Again, that has an impact on the checksum. Pings are particularly difficult. ICMP as a protocol is different between IP4 and IP6. It's a different protocol number. All of the types and codes in there are different, and there isn't a one-to-one mapping between them. And they've changed the way the checksum is calculated even, which just makes it that little bit more fun. So thinking about just normal packets, TCP, UDP, pings, we can change them and map them backwards and forwards. You then run into ICMP errors, and suddenly the whole problem starts again. An ICMP error, not only do we have to change the headers of the error packet itself, and we have to somehow map the types and codes, the different types of errors between the two, and there isn't a direct mapping between them. You also have the fact that the error quotes the original packet, so that the far end knows what packet went wrong. And that packet, of course, needs to be translated back again. So by the time this gets into the IP4 world, you get an IP4 error quoting an IP4 packet, the one you made up. So you've got to translate that as well. So you've got to do all of this again with the quoted packet. Of course, it's the other way round. You can't use the same functions because your source and destination are swapped round. This is the packet you sent. It's not a reply packet. Just to add to the fun. And then, of course, if the quoted packet is a ping, you've got all of the changes you have to do to the ICMP, which is different codes and types, and the fact it's different checksums, inside the quoted packet, inside the ICMP error. So you're down sort of 4 levels down of complexity here. And of course, all those changes in the quoted packet then change the checksum in the error again. Now, what we've tried to do all along, checksums are a little bit of a fun and games. We're actually trying to adjust the checksum, and we've managed to do this everywhere. So we don't recalculate the checksum of the original packet, partly because in some cases it involves all the fragments, but just for speed reasons, we don't want to have to load the whole of the packet into memory to calculate the checksum. So what we do is we adjust the checksum. We subtract the old IP address from it and add the new IP address to it, and makes the coding complicated, but means the actual processor takes less time forwarding the packets. So there are issues because we're doing mapping, and it's worth reiterating these. We've got to do session tracking, obviously, and the only way we can map these reply packets back to the original packets is to track the sessions. And session tracking isn't easy. TCP, well, it has SYN packets at the beginning, FIN packets at the end. Not too hard to track sessions. You've still got to allow for sessions that just vanish and time them out eventually, but you can track them mostly. UDP, unfortunately, is nowhere near as simple. You need timeouts. And the problem with UDP is it's used in different ways. There are protocols like syslog, which are fire and forget. You send a UDP packet one way and never get a reply. There are protocols like DNS where you send a packet and it might take seconds in some cases, but you get a reply and that's the end of it. And there are protocols like SIP where you get a stream of packets constantly. So in some cases, it's difficult to make a general timeout that works for all UDP cases. You have to consider a different timeout whether you've had the first reply or not, for example. And what we've done is all of these have configurable timeouts, an initial timeout and an ongoing timeout for each protocol that we can configure per port, per protocol, per destination, so that we can fine-tune the session tracking to actually match requirements. I've already mentioned you have to do a lot with ICMP errors. The session tracking, of course, is not based on the error, it's based on the quoted packet. So back to the fun and games of that. Another general mapping issue is that it hides the real identity of the session. It hides where you're really talking to. And is this a feature or a problem? Well, it's an interesting one for the Digital Economy Act that's coming up later, because the address you see isn't the subscriber's IP address. So when you get a nice little copyright infringement report quoting the address, you file it away in rubbish because it doesn't quote a subscriber IP address. So some people might call that a feature. One of the other problems with any sort of mapping is protocols. Well, there's two key things. Protocols that aren't TCP and UDP and ICMP, protocols that don't have built-in demultiplexing like ports. And the other is protocols which quote IP addresses in what's actually being sent. Now, the classic example is FTP, where the connection will quote the IP address to connect to for the data. We've actually found FTP will work if you can use extended passive mode, because it doesn't quote an IP, it just says connect to me at this port. And the other end connects to where it thinks it's going. The IP6 address gets translated, and it does get to where it's going. So it can work even for FTP. But if you really want to do it, you're going to have to put some sort of quite complicated assistance on a per protocol basis. And that's never going to be possible to cover every protocol. I've seen consumer routers that make an effort at this, and they list hundreds of things, including things like Age of Empires, if you're playing as a game. It has protocol assistance for it in the router, that sort of thing. So it's crazy if you really want to try and do this. We've chosen not to. We've decided that our box is just routing at a packet level. It's not going to try assisting anything. Obviously, as soon as you start session tracking, you've got a single point of failure. Everything's going through one box. If it breaks, you lose all the sessions. It's got a resource limit. As I've said, ports are a problem. You run out of them. So someone could use this as a way of exploiting it. Session tracking is difficult with timeouts, so make sessions that don't finish. Fill up the session table as a DOS attack. Use up all the ports. So you've got to think about that in the design. How do you address that? I've mentioned that the headers don't map exactly between each other. So someone trying to do something clever with IP4, prioritizing packets with particular DSCP markings, might not have the same meaning when it goes through to IP6 or the other way around. I've already mentioned not all protocols work. So, if you think that's hard enough, you then get onto fragments. IP4 packets can be 64K long and be chopped up into little bits. And they arrive as fragments, 1500 bytes long fragments, and we then go and put an extra header on the front, an IP6 header, and it's too big. So you've made a fragment that was there already too big. So we have to handle these fragments. Now, the first thing is, it is possible to map between IP4 and IP6 fragments. IP6 has a separate fragment header. IP4 has it built into the standard header. And it's possible to map them across and create the same fragments. But you're running into this size issue. So what we chose to do is, in one direction, we treat our IP6 side as if it only had 1280 MTU, on the basis that that should get through to the endpoint without any problems. So we fragment the IP4, fragmenting the fragments again if necessary, to 1280 in that direction. Then we pass the fragments through as IP6. So that should avoid any errors coming back on the IP6 side. Of course, it's possible someone implements an IP6 stack knowing full well that you should never see fragments in TCP, because it's the remote end that generates the packet, and TCP would always generate a smaller packet rather than a fragment. So you could have stacks that just won't cope with IP6 fragments on TCP. It would be an odd stack because most are written to have different layers for the IP and the TCP protocol, but it's possible. The other side, we mark the IP4 packets as don't fragment, which means, sorry, as we map the IP, we turn off DF, I think. Yes, we set the IP4 packets as don't fragment. We don't set the bit, which means they will get fragmented to get to the far end. So we shouldn't get any errors that way around either. Now this means we shouldn't have to cope with any errors saying the packet's too big, thankfully, because that would be a nightmare to map between the two sides. Partly because if the IP4 side said you can fragment it and we're now saying you can't, it's not expecting an error. Now, all of these cause problems. The IP protocols are well defined, but we've already seen as an ISP, if you generate fragments, some firewall will drop the fragments, and you won't get through, even though you should. We have seen that if you generate ICMP errors, some firewall will drop the errors, and the sender won't see them, and it'll keep sending packets that are too big. So fragments are bad news for everybody. So apart from these measures to try and avoid errors, we also adjust the MSS negotiation on the TCP sessions to make them small enough to get through this process without generating fragments in the first place. A lot of messing about to get that to work. There are other ways of handling this. I did a bit of looking at Wikipedia and came up with this list, and interestingly didn't come up with the next speaker, address family translation router, so sorry about that. So yes, some people came up with the idea of stateless IP mapping, where you just change the IP headers, but you're left with needing an IP4 header for IP4 address for every IP6 address, and we're back to running out of addresses. Some people thought about mapping IPs only, but with session tracking and not changing the ports, but that's not going to work because you can't handle two different people accessing the same site. NAT-PT, yeah. You then get into port mapping, which is what we're doing basically. The final idea, which seems to be quite popular, is a transport relay translator, and this is where instead of trying to do it at the packet level, you actually make a proxy. You have a device that answers for port 80, understands HTTP, or at least understands TCP as a complete protocol stack, and feeds it through the other side. This has lots of advantages. It avoids all the MTU issues because they're negotiated separately each side. It allows you to add extra support for protocols that have embedded IPs. But it's a lot more work for the box. You have to implement a complete protocol stack on each side. You have to have all of the buffering for TCP for every session on both sides. You're not working on a per packet basis. So you're not going to make a piece of kit that can handle things at the sort of scale ISPs want anywhere near as easily. Now, one possibility we came up with is you can mix both ideas together. We can make something like our router where we're translating at a packet level, and we then have special cases where we understand certain protocols need assistance, and we redirect those to another box that does TRT. So by mixing the two together, we can have the high efficiency, high volume pass TCP packets for protocols that don't care, like web pages, and divert traffic that needs extra help to another box, or multiple other boxes. Implementations, this is where I left out the next speaker. There appears to be a NAT-PT available, which has plugins to help protocols. There's a PTRTD. CAME have come up with something called Faith, apparently. I don't know much about these, but there's lots of people trying to make this work in different ways. Trick or Treat Daemon, I already mentioned. It has its quirks, and I think we'll be writing our own eventually. One of the things I want to do, which would have been quite fun for this event, is I want it to pretend there isn't an IP4 address. At the moment, when you ask it for an address, it gives you IP6 and IP4. It'd be quite nice if it didn't give you the IP4 at all and just said, no, there's only an IP6 world out there. IP4 went away. Very useful for Mac users, because Macs seem to pick IP4 and IP6 randomly, and yeah, pain in the neck. And of course, there's lots of commercial solutions. You have people like Cisco have solutions, obviously, and there's us. So, now, redundancy and scaling I was asked to put in. Any session tracking box is going to have issues because it's a single point of failure. And you either have to make multiple boxes that can keep state between the boxes somehow, or you put up with the fact that if it crashes, you'll lose the state and sessions will break, but another box can take over. You could do some sort of load sharing based on hashes, potentially, because if the same IPs always go to the same box, you can handle it. But that falls down when you have ICMP errors, because the ICMP error is quoting an intermediate IP at you, not the original one. So a switch using hashes to load balance between different boxes isn't going to work for that. So it's quite tricky to do on a large scale, but it's not impossible. It's certainly possible to have a backup with VRRP to take over if something breaks and drop sessions in the process. Security. Well, obviously anything you're doing with this has got to be locked down to some extent. You probably want only your customers to access this gateway. Otherwise, you're making a gateway proxy that anybody in China can access. At the moment, we've left it open, largely so that you can try it out. Our customers have been using it. It's quite fun. You probably want to block some IP4 targets. When I first put this up for our customers to play with, it allowed 127.0.0.1, so they could get to the login screen on the box itself by talking to that, which was quite fun. Couldn't get any further, but it was interesting. Good idea to keep some logs, obviously, for your own use. They can get very big, though. It's like any NAT or session tracking box. If you want to log everything, it's huge. And obviously, you have to be very careful writing the software with this. You need to allow for the fact that packets might be accidentally or deliberately broken. They don't necessarily follow the spec. And you need to avoid any exploits. Legal implications. Well, we don't actually have to trace the sessions yet. Even the Data Retention Directive doesn't require that, and the Digital Economy Act doesn't require that. So thankfully, we don't have to trace sessions, and I really hope the day doesn't come when the government think that's a good idea for ISPs to do, because it's far too much data to do. We might want to do it ourselves, obviously, but if you were to trace sessions and someone wanted to complain about a customer, you've got the whole issue with not only IP addresses, but IP addresses at both ends, ports at both ends, because we're overloading the ports. You've got the need for very accurate clocks. If someone complains about a particular IP and port 1 second, it might be a different customer the next second. Okay, might take a few seconds to expire things, but it could move very quickly. It will depend on legislation and what's practical, what we have to do. Now, thankfully, we don't have to do anything nasty with this. One of the fun things, of course, nothing to stop you running a box doing this in another country. It gets very fun with what the law can make you do then. But thankfully, Digital Economy Act, which we'll hear a lot about later, does require a subscriber IP address. And my NAT-64 gateway doesn't have one. It has one of our IP addresses. So, oh, it's gone off the bottom. What a surprise. Does it work? Well, we turned it on. And we told customers about it, and they all think it's great, but they're a bit geeky at the best of times. They're probably watching this now. If you'd like to try it, you can set your DNS to that, 211.8p0.6464:1, and that will point to our trick or treat daemon. It will give you IP6 addresses for any IP4 hosts. Now, I tried to do this on my Mac. I have no idea how I convinced my Mac to use a different resolver. It's buried in there somewhere. They make lovely boxes, but I don't know how they do it. There's also 217.169.2026, which will do it if you want to put an IP4 resolver in to get your IP6 addresses. And that should work for you now to try. It works with TCP. It works with UDP. It even works with ping and traceroutes. And this took me ages to get working. It even works if you do really big pings that are fragmented and have to be refragmented into twice as many fragments to get through. It works. The last bit here, very proud of this. The traceroute through the gateway even works on Windows. I was amazed. It works on my Mac, it works on Linux, it works on Windows. This is a traceroute that started from an IP6 host trying to access BBC Co UK, which doesn't have an IP6 address as far as I'm aware. It got our fake IP6 address for them, 211.8p0.6464.0.666 and 616, because NAT is evil. D43A-E08A is hex for their IP4 address, so it's embedded in the address. Don't ask me why the first hop didn't work. I really didn't bother working that one out. It then went through several of our gateway routers and eventually got through to one called Armless there with an IP6 address quoted. It then got to nat64.discard.me.uk, which is my NAT64 box. And you'll notice it quoted an IP4 address there, : 9155.46.46. And then it's going through the rest of the IP4 world to get there. 9155.53.6, 193.203.590, and so on. And what I was impressed with is not only does Windows quote those as IP4, because they're just zeros in the front and then IP4 on the end, it actually did the reverse DNS lookup to quote the names based on the IP4 address. I'm really impressed with that. And then finally, it appears to get to its IP6 destination, this made-up address for the BBC. So traceroute actually works through this. That's the last slide. Any questions?
I have a question, Adrian. Sorry, on what you've had in the package, will that have effect on negative effect on certain applications? I'm thinking online gaming in particular.
I'm going to be really impressed if any online gaming ever works with this. But I'm not sure I quite understand the question, though.
If you have to do something with a packet, then obviously you have to examine the packet, which is going to slow it down.
Are you thinking latency aspects in terms of this? Yeah.
Ordering as well.
Oh, reordering. Right. Well, what we're doing, we're not introducing any packet reordering or excessive latency. This is, I mean, in our case, the router is only doing slightly more than it would normally do with a packet. It is having to tinker with a few bytes on the front, but it's bytes that are already in the cache in the memory anyway at that point. So it isn't really adding particular latency. The biggest latency increase will be the fact that the packet is taking an unusual route, going all the way to the gateway, and then from the gateway onto the final destination instead of going directly. It will go through different hops to get there. But I can't see it having any particular impact if ever any online gaming actually works with this. But we're just waiting for World of Warcraft to start working with IP6. I think it's going to be great fun. Any other questions? Oh dear. Okay.